Now if you're in my class and working independently, then go ahead and take care of these instructions when asked to create the sliders. As you type those things in, say yes, and record any of your own notes or observations. But for most of you, if you're watching this, this means we've already looked at this as a class, and it would be time to move on to the next step. So here is what we are dealing with. In the key concept, we're talking about graphing systems of equations. And before we get too deep, what we need to understand is that we, in the past, have done equations and turned them into lines. But if I had, two equations, I would have two lines. And I guess they could be parallel. They could be perpendicular. They also could just intersect at one point. So with the ruler, let's draw two lines that intersect only at one point. So this would be the line that would be represented by one equation. And then here's another one. And make a closed circle there to show that they run into each other at only one point. And when we're asked how many solutions this would have, we would have exactly one solution. I'm going to write SOLN to keep that shorter. Pause at any point if you need extra time. Now, because these lines intersect, and I could also say they coincide, they kind of run in together, for the terminology, we're going to start by saying they are consistent. So what consistent means is that they intersect somewhere. And then we're going to have another term in a moment that I'll explain later, just because I only want you focusing on the fact that they're consistent. Now the other case that you might have is, you could have a line whose equation is the exact same as another line. And I drew this in red because if you draw two lines on top of each other, it's not like you're going to really see them. So let's make a little star here that even though you see one, it's actually going to be two lines. And what this means is that if these lines run into each other here, they also run into each other there, and there, and there. So it's not like these two lines only have a single solution like they did earlier. This would have infinitely many solutions. SOLNS. Now, just like this one, where it was consistent because it had a solution, now these two lines coincide, so I will also say that this line is consistent. And actually I said this line, but I should say this system of equations is consistent. But we're going to save that other term again still. Well, we had a situation where they ran into each other, and the word for that is that they intersect. We have a second case where they're the exact same line. And then we have another case where they might never run into each other. And so these would be parallel lines. If you think you need to remember that, you can write a little note here, parallel. And what this has is no solutions because they never run into each other. And what this means is that since they don't run into each other, they are inconsistent. They don't consist. Now as we look at this, kind of just save the consistent, and inconsistent term for the, mention that first, and saving this other term for now. And the new term would be dependent and independent. So consistent and independent, whenever there's only one solution, that means it's going to be independent. And if there's infinite solutions, there's dependent. But here we wouldn't bother with anything because there's nothing to be said. And I think earlier I was talking about perpendicular lines. Well, There wouldn't be a special case for perpendicular lines, and that's because it would still just be one solution. They would only intersect at one point. So in summary, you can intersect at one point, an infinite number of points, or no points at all. There's really no other possible solution to that. And since this is heading towards 5 minutes, I'll break this apart and save this for number 2. This will be video 2.